Okay, so we can start, I think. So this is the big seminar of the combinatorial geometry group, and it only features the big stars in the subject. And Pavel is essentially the head of the combinatorial geometry group in Prague, in the absence of Jirka Matušek. Jirka Matušek is to some extent also present in our group because the reading seminar is named after him. Anyway, Pavel has done a lot of beautiful work in combinatorial geometry for a very long time, and the subject of this talk is a classical topic in combinatorial geometry, this force and island. So thanks for accepting our invitation.
Thank you very much. Thank you very much for the very nice introduction. I think it's, if I look at the names, there are mainly two stars for the future, Martin Balko and Manfred Scheucher, who are the co-authors of this work. And this will be about point sets, about random point sets, and if we have a point set for a random point set, really, let's stay first in the plane. So the points are in the plane. If the points are chosen, let's say uniformly at random from some bounded region of positive area, then with probability 1, there will be no 3 points on a line. So this I will suppose during the whole talk. And now for a point set, what could be a convex subset? So usually by a convex subset, we mean, now let's see, okay, that's impressive. So by a convex set, sorry for the drawing, those should be straight lines, those five segments, or straight line segments. So by a convex subset or convexly independent subset, we usually mean vertices of a convex polygon, or there are other ways how to say it. And but on the other hand, for a point set, there might be another definition of a convex set. We might take a convex region in the plane. We may intersect it with our point set, and then the points which are inside, in our case here, it's 8 points, which if I count well, those 8 points, they form in some sense also a convex set, but it's not really a convex set. It's called island in that case. And if we have both properties, that a subset of our point set is convex and it's an island, then it's a whole. So for example, these 5 points, I will connect them like that. Those 5 points form a 5 whole, because there is no point inside. Here, those 8 points, they form an island, but not a whole, because the convex hull contains now the drawing is really strange because these 2 points are inside this body. Maybe now I should add this, make some funny picture. Okay, so this was roughly what we will be talking about, and we will concentrate on holes and islands, and we will show that there are not too many of them in a random point set, and not only in the plane but also in higher dimensions. There is some easy lower bound for the number of holes of some fixed, rather I should say island, for the number of islands of some fixed size. We will always talk about holes of or islands of some fixed size k, and for at least for islands there is an easy lower bound in the plane, quadratic lower bound for the number of k holes for any reasonable fixed k, and we will see that this bound actually is achieved by random point sets, asymptotically achieved. So let's see if I can move to the next slide. So during the whole talk, as I said, we will have a finite point set S in the plane, sometimes in higher dimensions, in general position, meaning in the plane that there are no 3 collinear points. Then I cannot move. That's okay, so here is a picture for that, and I should go to the next slide. So here is what we mean by a k-gon. On the left we have a k-hole, 5-hole. On the right we have a 6-gon, which is not a 6-hole. And the classical theorem by F' and Scheucher says that for every integer k, there is some big number such that every set of that big number of points contains a k-gon, k points which are vertices of a convex k-gon. Now the points are in general position. The smallest integer which satisfies the theorem is denoted ESK here, and sorry, maybe I should let's see if I can really write. So if k is 3, then the f' Scheucher number is also 3, because if we have at least 3 points, we find 3 points which are vertices of a convex triangle. For a four-gon, convex four-gon, we need 5 points. 4 points are not sufficient because if we have 3 points and 1 point in their convex hull, we don't have a convex four-gon, but for 5 points we do have, because either the convex hull itself contains at least 4 points and they must be in convex position, or the convex hull is a triangle like here in the picture, and the remaining 2 points are inside. In that case, if we draw the line through those two points, then at least actually exactly 2 of the convex hull points are on the same side of the line, like here, these 2 points, and they together with the two interior points form a convex four-gon. Then for k equals 5, if we have 9 points, we know that we have a convex pentagon, and we sometimes need 9 points. 8 points are not sufficient. for 6. This was known and proved several times. I think in the 70s, I believe, in the previous century, and for 6 we need 17 points, which took more than half a century to realize that. It's a result by Peters and Sekeres. And if you look at those numbers for general K, you may conjecture that the actual number might be 2 to the K minus 2 plus 1. And that's exactly a conjecture of Erdős and Sekeres, which is still open. There is a theorem due to Erdős and Sekeres from 1960 that the Erdős-Sekeres number is at least this number. There is an explicit construction, and for an upper bound, for long, the upper bound was roughly 4 to the K, and it was a big open problem if the base of the exponent is 2 or 4 or something in between. Now, due to Andrew Sook, we know that the base of the exponent is 2, and actually there is a paper by János and his co-authors which somehow improves the lower order term, but still the exact bound is unknown. So this is some very quick history about this result. Maybe any questions at this moment? So if not, usually I ask my students if you hear me, but I see people laughing, so hopefully that means that everything is okay. Hopefully, cannot still move this way. Sorry. So a K-hole, I explained the definition. So here is again a picture of a 5-hole and of a 6-point subset, which is not a 6-hole because of the point inside. Here is the formal definition, and the Erdős was first to ask something about holes, and he asked if every sufficiently large point set contains a K-hole, and it was expected to be true, but in fact it is not. So for here is again some small values are known. 3 points are sufficient for a 3-hole, that's obvious. Let's say 3 leftmost points are always for a 3-hole, even if we have more than 3 points for 5 holes. For 5 points, by an argument similar to what I showed, there is always a 4-hole for 5 points, and therefore for at least 5 points as well, because we can take the leftmost 5 points, we find a 4-hole in that 5-point set, and that's a 4-hole in the whole set. Now, Harbord next value of K was determined fully by Harbord, who showed that for a 5-hole we sometimes 9 points are not sufficient, but 10 points are always sufficient. 10 points in general position. So here there is already a difference because 9 points are sufficient for a convex five-gon, but not for a type hole, and there is a really huge difference if k equals 7, because there is no Ramsey type or Erdős-Szekeres type result in that case, which was showed by construction of Scheucher from 1983. It's relatively simple, but difficult to draw. We didn't draw it here. Line now, and for long it was open if there is always a 6 hole in a sufficiently large point set in general position. There is no question, right? It's just somebody is unmuted. There is so this was proved by independently by 2 PhD students almost at the same time, by Gerkent and Nicholas. And once we know that there are holes, k holes for k up to 6, we may ask how many are there. So this is another thing what people study. And of course, if the points are in convex position, then every k element subset is a hole, and is a hole. So therefore, we may have as many as n choose k holes, but much more interesting is to ask for the minimum number of k holes, and that's counted or taken among all sets of endpoints in convex position. This was the first paper, I believe, was by Imre, Bárány and Füredi. They showed that H3n and H4n is quadratic, and that the function H5n is big O of n squared, and actually also H6 of n. The best upper bounds for these four functions, H3 through H6, were given by Imre, Bárány, and by myself. Concerning the lower bounds, as I said, there is a quadratic bound, lower bound by Bárány and Füredi, and for H5n, there is a relatively recent improvement over the linear lower bound, which is just by this logarithmic factor, so it's quite widely open what is the order of magnitude of the function h5. For the function h6, we get the linear lower bound by the result of Gerken and Nicholas. This is because if we have our point set, we may partition it into parts, each containing sufficiently many points, but constant number of points, so that it contains at least 1/6 hole, so 1/6 hole here, 1/6 hole here, and so on. This gives us a linear number of 6 holes. Maybe the constant is not very good, but it gives a linear lower bound. but this is the state of art for H6, and for Hk of n, there are it is always equal to n due to the construction of Horton of point sets, arbitrarily large point sets with no 7 hole. Maybe any question at this moment? Okay. So I start to talk now about higher dimensions for a while. So in d dimensions, there is a d-dimensional version of Horton sets in any fixed dimension, which contains no k-hole for sufficiently large k. So we fix the dimension, and we find for any n, we find a point set of n points in general position, which contains no k-hole, where k depends and heavily depends on the dimension, but not on the number n. Okay, so this is this result. So again, like in the plane, there is no Ramsey type result for holes, but for sure there are always in d dimensions holes of size 2d plus 1, so size 5 in 2 dimensions, actually 6, we know, of size 7 in 3 space, 9 in 4 space, and so on. And for the smallest reasonable value, which is value of k, which is d plus 1, the minimum number of d plus 1 holes is known to be of order n to the d, which was proved again by Bárány and Füredi. So this is the result which I was mentioning for 4 holes. Sorry, here is d plus d plus 1. So in the plane it would be for 3 holes in the plane, and this is what we get in general dimension here in this very special plate. And what we did in our paper, we considered instead of fixing, we didn't fix the dimension quite, or we fixed the dimension, but it could be bigger than 2, and we allowed this number b plus 1 to be replaced by any constant k, and we allowed instead of holes to consider islands, and for that we still have the same upper bound n to the d. That's the main result, which will be explained in a more proper way on the next slides. Again, any question? Everything is okay. Janos, everything is okay. Do you hear me well? Do you see me well? Should I stay with the video on, or should I switch off the video? Is it fine like that?
Perfect.
Perfect. Thank you very much. Thank you. So this is exactly what I said, that we will get this upper bound, and it's given by random point sets. The points will be chosen from any fixed convex, let's say bounded convex region of positive volume or volume 1, let's say. So we need some notation. Here, this terrible notation is about the expected number of holes in a point set of n points in d dimensions, and we are in the convex region, or there is written convex shape K, which has, let's say, volume 1, and K is the size of the holes which we are looking at. So K should be typically at least d plus 1, but fixed. D is also fixed and is going to infinity. And on the next slide there will be some more, little bit more information. So the previous result of Bárány and Füredi, the upper bound was about d plus 1 hole, so empty simplices like triangles in the plane, tetrahedra in free space, and so on. And the upper bound, I said that it's for the n to the d, also the lower bound, and in fact here we see the constant which they had, which we somewhat improved, which we will see later. So next slide is here. So here in particular there exist sets of endpoints in r dimensions with this number. This is missing here. I noticed when preparing the talk, with this number of empty simplices, only with this number, and they are the random point sets. This result, which was already known in the plane, and it was achieved for Horton sets. So our results, as I said, we extend the bound to larger holes and even to islands. So here is a formal definition. An island in a point set S is a set which, if we take its convex hull, like here on the picture, and intersect it with the set S, we get the whole set. So here is a island of six points, those white or red points as you like, the 6 points. Here is again comparison with a convex polygon and with a hole, which is also a special type of an island. Any question at this moment? Okay, good. So here is formally the result which I was indicating. There is the the constant which is the constant which we obtain. So we fix the dimension, we fix the size of the island, we fix a convex region K of volume 1, and now S will be a set of endpoints chosen uniformly and independently at random from our convex region K, and then the expected number of islands of size K in S is bounded from above by this terrible expression, which is order of order n to the d. If you look here, this is independent of n up to here, this part. So this is a constant for us. And here, the fraction on the top, we have on the top, we have n to the k minus 1 order of that, something of this order. On the bottom, we have here this extra minus d, therefore this fraction is of order n to the d. This constant actually, it will be mentioned later, can be improved if we look only at the number of k-holes. Remember, k-holes are special types of islands, so we may expect fewer of them, the same number or fewer of them. So let's see what is here. Here, the bound from this theorem is asymptotically optimal. Why is it so? I will explain first in the plane. In the plane, let's consider point set, and now choose any 2 points in our point set. Let's say this point and this point. If we take the lines through them, sorry, it's not quite a line, but this should be a straight line. Then if we take that line, and if we take k minus 2 points, which are closest to this line, which might be maybe this point here, then altogether these 2 points plus the k minus 2 points surely form an island, because they lie in some slab. So therefore every pair of points is a subset of some k island, and because we have quadratically many pairs, this will give us quadratically many islands, because we count every island at most k choose 2 times, because every island has k points, at most k choose 2 pairs. So if we don't care about the constants, this is a lower bound of that order for islands, and it works pretty much the same way in higher dimensions. Let's say in 3 dimensions, instead of a pair, we would take a triple. We would take the plane which contains this triple by the general condition, general position condition, which I actually forgot to explain in higher dimensions. There will be no point on that plane, or with probability 1 in our case, I could say, and we take again now k minus 3 closest points to this plane, and we get a k island, and again each island is counted this way at most. Now k choose 3 times, so this would be cubic lower bound for islands in 3 space, and you can imagine the argument in an arbitrary dimension, this triangle replaced by a simplex, this d plus 1 points. Okay, so maybe I will say that the general position in d dimensions means not only there are no 3 points on any line, but there are also no 3 points on a line, no 4 points on a plane, no 5 points on any 3-dimensional subspace, up to know how many b plus 1, b plus, should I say b plus 1, no b plus 1 points on any hyperplane. Okay, as I said in the previous theorem, this terrible expression, the constant can get better and nicer, and this also improves somewhat that bound by Bárány and Füredi for the number of empty simplices, which was roughly d to the d square. Here it's something like d to the d log d. Oh, sorry, d to the d. Okay, and there are some other results which were known before, some special results, like for 4 holes in the plane, we have this better constant. This is actually our what we get from here, and it improves the previous constant by Fabila-Monroy, Huemer and Mitsche. Sorry for wrong pronunciation. Any questions at this moment? I hear so many questions as if I teach by using Zoom. Hopefully everything is fine. Okay, so the slide again. What we have additionally here is that very recently Reitzner and Temeshwari put on the web paper where they show asymptotically tight bound for the number of p plus 1 holes of empty simplices. For the plane, that the constant is 4, I believe. Yes. 4 times n choose 2 is the asymptotically the number of empty triangles, and if and also they obtain a tight bound for the special odd value of k in any dimension in case k is a ball or equivalently, essentially equivalently an ellipsoid, because always all these questions are of course independent of affine transformation. So therefore ellipsoid results for ellipsoid must be the same as for a ball. They are equally strong. So here is again the first two lines are the same, or points are the same, but what I already indicated here, this our result, we get this upper bound which cannot be obtained by the d-dimensional analog of our concepts, and I believe there will be, yes, there is the exact theorem 3 for that statement. For holes, we know that if k is really large, then there may be, sorry, now I have, for the previous slide was talking really about holes. Now it's not about holes, it's about theorem 3 is about islands, and it says it gives a lower bound for the number of islands, which is at least k if k is not too large, and in the exponent at least k, and at least exponential in the exponent if k is larger than exponential. So remember that for random point sets, we have here just the dimension b in the exponent. So this gives a distinction between Horton sets or the dimensional Horton sets and random point sets, and that's a difference compared to the plane. In the plane, both Horton sets and random point sets give the quadratic upper bound. Then if k is not more than this exponential number, then H even contains at least k or exponentially many k holes. And as I said, we have to have something like this here in the exponent, the minimum, because for really large k, we have no holes. Any question here? This is
one short remark. There was a recent paper by Book, Chow, and Holtzman who further improved the Horton set construction in higher dimensions.
Yeah,
I didn't. Yeah, maybe you have some more details.
Thank you. I don't have more details. If you wanted to say, this was Manfred Scheucher, the courser who helped me now. Can you say the names of those people who did it?
I can write them in the chat. It's Book, Chow, and Holtzman. I think Holtzman is even in the audience.
Okay. Yes. Okay. So if I say, maybe you can say it better. If I remember well, here you constructed point sets where there are no k holes for k exponential, some large exponential function indeed. Is it correct?
Yes.
So that means that this complements quite well this result, because up to an exponential function, we have as many k holes as we can, asymptotically as many k holes as we can expect, and to the k, then there is when k is exponential, we don't know, but if it's more than exponential, then by your result, there are no k holes. I hope I'm saying it correctly. Okay, so here is, sorry again. So here is the, and here comes the idea of the proof. It's exactly 7 in Prague and 8 in Moscow. I believe. Do I still have some time? On how much time? Can someone tell me?
You have infinite time.
Infinite. Okay. I have some slides from other talks. Okay, so I will try to explain the idea of the proof on these slides. So we have so here we repeat what we really want to prove. We want to prove the main theorem. So we want to prove. We will be in the plane that I forgot to say. Maybe it's here. It's not here. It's not here. So we will. I will talk only about the plane. And so we want to prove the quadratic upper bound. In this case, it will be n to the d on the expected number of k islands in a set of S of n points, which are chosen uniformly and independently at random from a convex region K of area 1. So, for example, inside a square or inside a disk unit square. And so, suppose we have an island which is now here in this picture down here.
Can you zoom out a little bit? I think it's better than.
Okay, I will try.
Even more.
This will be okay. Thank you for so sorry for really. I may try once more, but I don't know. It's because of
It was fine. I think it was fine.
I just tried if it doesn't work to jump page by page, but it does not. Okay, so suppose we have an island. So these are, here is a picture of 12 points, P1 through P12. So if we take the convex hull of all these points, there will be no other points from our ground set. There will be some points around. Probably I should use. Make it. Okay. So there are points around, but none is here inside the convex hull. And now we want to get something like a canonical order of those points. How the canonical order works. So the first 3 points, P1 through P3, will be the vertices of the largest triangle determined by our island. So our island I is a set of points P1 through P12 in the picture, and we want to give something like a canonical order for them, and so there are various triangles like this one, which has certainly smaller area. So we compare areas, and it has certainly a smaller area than P1, P2, P3. Supposedly also this triangle, which might be the second largest triangle in this point set, I'm not sure. And there are other triangles like this one, for example, and they are all supposedly smaller than P1, P2, P3. So this is how we determine P1, P2, P3. I will not tell you how we exactly order these 3, but they are like that. Now I will try to remove this, and then there are points P4 through P7 in our picture. So P4 through P3 plus some number A, which is between 0 and K minus 3, I believe. And those points are inside. So these are P4 through P7. We may order them, let's say, from left to right, like on the picture. And then the remaining points, they lie outside of the triangle, and we order them according to the increasing distance to the triangle delta, to the triangle P1, P2, P3. So P8 is very close to the triangle, P9 also quite close, and P12 is quite hard. Okay, so this is this gives a unique order, or certainly on the points P4 through P12, and also in some way P1, P2, P3. And now we want we want to estimate the probability that our points which are P1 through Pn, our point. So we chose points P1 through Pn in the convex domain, and we now want to estimate the probability that the points P1 through Pk will form an island, and the order which is here, this order P1 through Pk is that canonical order which I just explained. This probability we want to estimate. We will prove that that probability is of order 1 over n to the k minus 2, and because we have n choose k. Sorry, not n choose k. We have n times n minus 1, etc., n minus k plus 1 ordered k tuples of points in our point set, and for every k tuple we must have the same probability that those points are form an island, and they are ordered in the canonical way. Is this clear somehow? Now it might be a bit confusing that once I'm talking about P1 through Pk, about a specific k tuple, and once about the first k points which we choose from our point set. But we just estimate the probability for this one particular k tuple from our ordered k tuple from our point set, and we know because the points are chosen independently and uniformly that actually the probability must be exactly the same for any other k tuple. So for all these roughly n to the k k tuples, so we have roughly n to the k tuples, ordered k tuples. Each of them forms an island with the given canonical order. This is probability. So if we multiply this number by this number, we should get an upper bound on the we should get an upper bound on the total number on the expected total number of islands of size k. Is this clear? Thank you, Janos. This is very good. This is my students would never do this. They would just make no reactions. Okay. Still any question at this point? Okay, so hopefully this is clear. And now I have infinite time, but I think I should not talk too much longer. So how do we prove? Here is first. Here is some picture actually which shows that once we draw the triangle and we are adding the points, imagine that we add the point P8, then this shaded narrow shaded triangle must be empty, and we still don't know about the other points. Now P9, where P9 can be. P9 must be outside of the convex hull of the points seen so far. So that might be this convex hull. P9 must be somewhere outside, and the difference between this convex hull, which I drew here, and which is the convex hull of all the 9 points. So this triangle here, this narrow triangle here, must be empty. So this is the condition on the point P9. There is also an additional condition on the point P9 that it must be inside this bigger triangle, because otherwise it would form a bigger triangle with 2 of the points P1, P2, 3, bigger triangles than the triangle P1, P2, P3. So P9 cannot be here, for example, because, and none of the points actually, because then this triangle P2, P3, P9 now would be bigger than P1, because this is if we take this as the base of the 2 triangles, then the height of this triangle would be bigger than the height of the triangle P1, P2, P3, and so this